When we talk about computers, we're almost always obsessed with one thing: speed. But how processors got so mind bogglingly fast? Well, it's not just about making them bigger or cranking up the clock speed. It's this incredible story of engineering, creativity, and some really clever design. Okay, let's get right into it.
So let's just start with the most basic question, right? You've got two different computers sitting on a desk. What is it really that makes one of them a lightning fast powerhouse and the other, well, not so much? The answer is probably not what you think.
Because here's the thing, it isn't just about raw speed. It's all about the underlying strategy. It's the architecture, the philosophy that decides how a processor is going to handle the millions upon millions of instructions we throw at it every single second.
And to really get these strategies, we first have to talk about the most fundamental idea in pretty much every modern processor: the instruction pipeline. And honestly, the best way to picture it is just like a factory assembly line, but instead of building cars, it's processing our data.
So every single command your computer runs goes through these four main stages. First, the processor has to fetch the instruction from memory. It's got to go get the order. Then it has to decode it, to figure out what that order actually says to do. Next, it executes the command. This is where the actual work, the number crunching, gets done. And finally, it writes back the results somewhere useful. Four simple steps, repeated billions of times a second. It's wild. Okay, now this is where it gets really cool. Just look at this diagram. See how a new instruction, instruction 2, starts its fetch stage while instruction 1 is already moving on to decode? It doesn't wait for the first one to finish its entire journey. This overlapping, this assembly line method, is what we call pipelining. It lets the processor juggle multiple instructions at once, and that makes everything so much more efficient. All right, so now that we get the whole assembly line idea, we can jump into one of the first big arguments in processor design. It was a debate that basically shaped the entire industry for decades. Are you Team CISC or Team RISC? And you can actually see the difference in their philosophies right here. On the left, that's CISC, which stands for Complex Instruction Set Computer. The part to notice is that microprogrammed control memory. Think of that as a little mini computer inside the processor that can interpret really complex commands. Then on the right, you've got RISC, the Reduced Instruction Set Computer. It's all about speed. It uses hardwired control, meaning the logic is literally burned into the chip, and it splits up its memory for instructions and data to keep things moving fast. They're wired differently because they think about problems differently. And believe me, this was not some minor technical disagreement. As our source material puts it, these were two totally distinct schools of thought. Each side was completely convinced they had found the one true way to build a processor. This table really lays out the trade-offs. CISC is all about power. It uses big, complex instructions that can do a lot at once, but they might take, say, 2 to 15 clock cycles to finish. That's the architecture you'll find in most laptops and desktops. RISC, on the other hand, is all about simplicity and speed. It uses a small set of simple instructions that almost always finish in just one clock cycle. This crazy efficiency is exactly why RISC processors absolutely dominate the world of smartphones and mobile devices. But just making the assembly line faster wasn't going to be enough forever. The next huge leap in this whole quest for speed came from figuring out how to completely smash that one instruction per cycle limit. The answer? Parallelism. The art of doing more than one thing at the exact same time. So before we can understand parallelism, we need to know our starting point. And that's the scalar processor we've been talking about. Its whole principle is simple. One new instruction gets started for every tick of the processor's internal clock. It's efficient, for sure, but it's fundamentally sequential, one thing at a time. And here it is again, our trusty single-file assembly line. See, one instruction follows the other, nice and orderly. This is our baseline. But it leads to a great question. What if we could build more than one assembly line? And that is exactly the idea behind a superscalar processor. It's a design that literally has multiple parallel pipelines built right in. So by having more than one assembly line running at the same time, it can issue and start working on several instructions in a single clock cycle. This picture just shows it perfectly. This is a superscalar processor of degree 3 because it has 3 parallel pipelines. And you can see it right there, 3 different instructions all kicking off at the exact same moment. In the time our old scalar processor got 1 instruction started, this new design is already working on 3. It's a massive boost. But wait, there's another totally different type of parallelism. This one is purpose-built for the gigantic data sets you see in scientific research and supercomputing. It's called a vector processor. And instead of doing one operation on one piece of data, it's designed to do one operation on an entire list of data, all from a single command. Now, don't let the math formula here throw you off. It's actually super simple. V1 isn't just one number. Imagine V1 is a list of 1,000 numbers, and V2 is another list of 1,000 numbers. That single plus sign is one instruction that tells the processor, add the first number from V1 to the first from V2, then the second to the second, the third to the third, all the way down the list for all 1,000 pairs. And then it stores all those answers in a new list, V3. It's an unbelievably efficient way to get a ton of work done. This comparison just makes it so obvious. Up top, you see this scalar pipeline. Notice all those little gaps between operations? As the processor has to stop and figure out the next instruction. But now, look at the bottom diagram, the vector pipeline. It's just a continuous, jam-packed stream of data flowing through. Because you told it what to do just once, it doesn't have to keep stopping. For huge, repetitive jobs, the efficiency is just off the charts. So, after going through all these different designs, what's the big picture here? What does this whole quest for speed really tell us? Well, it really boils down to these core strategies. Pipelining gave us that fundamental assembly line. The CISC versus RISC debate forced designers to choose between powerful, complex commands and simple, lightning-fast ones. Superscalar designs just multiplied those assembly lines to do more at once. And vector processing completely changed the game for huge calculations. And I think that's the real takeaway. The evolution of processors isn't just a story about technology getting smaller and faster. It's a story about human ingenuity. It's about people finding these incredibly clever and elegant solutions to the unbelievably complex challenge of computation. For decades now, engineers have been masters at playing by the rules of physics, squeezing every last drop of performance out of silicon. But as we start to hit the physical limits of these designs, you have to wonder, what's next? What rules will the next generation of designers have to break to find that next great leap in speed? That's the question that's going to define the future of all of this.